All right, so just a reminder for you all, for all of you guys and anyone watching the video, we've got our Loop Quiz 3 coming up 1 week from today. That Loop Quiz covers sections up through section 4.6. So basically the only stuff that won't be on that Loop Quiz would be, like E's, LNs, arcsines, arctangents, inverse functions, but everything else. Okay, so everything else. That's a big chunk.
And limits?
Limits, yeah, everything. So from last August. Oh no. The reason why it's not just this semester is because in April you have to know all of it. There's no such thing as, hey, we'll forget that semester one it never happened. Yeah, you got to know all of it. So I believe there's a prep or two posted for that. And as always, if you ever run through the whole prep and you're like, wow, I could use more material, I have no doubt we could find more for you. So let me know. Let me know. Okay, so are you guys all right here on this? This right here. Okay, so what is different about this when we compare to the other two that we've done? The other two that we've done, you had a slope field or slope fields, and you were trying to compare those to differential equations. And this is a little bit different because if you take a close look at it, we are not comparing a slope field to differential equations. We are comparing the slope field to what? Solutions, yeah, solution curves. And so, you could transform this into, a bunch of differential equations. Like, how could you transform, like, option A into a differential equation?
It would be 2x.
It equals what? dy dx. Yeah, no floaties. We want to have, like, actual expressions that mean something. So, yeah, if you wanted to write dy dx equals 2x, you certainly could do that. That would be option A. So you could do that for all of them, right? You could do that for A, B, C, D, E, and that could work. I will say this, you don't have to do it that way. If you are familiar with what these solution curves look like, you might be able to do this without doing all that, but if you can't, that's okay, right? This will just take a little longer. So do what you got to do, whether you can just like tell what it is, and if you can tell what it is, you can probably tell that pretty quick. And if you can't, you're going to want to do the differential equation. So take a few minutes, discuss, try, and I'll give you the answer in a minute. I ahead and filled out all of those differential equations for you. But right at this point, I'm most interested to hear what your answers are. So I'm going to go 1, 2, 3. You just shout your answer. All right, ready? 1, 2, 3.
E.
Okay, so I heard things that ended in E. So I would say A is out. I definitely heard E. Did I also hear a B? I heard B and E. Is that correct? Okay, fair enough. So let's make sure that we're all clear maybe why we can eliminate some of the ones we can eliminate. We definitely can eliminate A. I'd love to hear from one of you guys. Like, what did you see about A that told you it's not A?
It's also the 6 and 3.
Oh, sure. Yeah, okay, I agree. So when X is 3, we're talking about out here, not 6, especially when you compare it to what would be happening over there if that were it, right? We should see an increasing pattern of slopes. And we don't. Okay. Fair enough. So A is out. We'll leave B because B was proposed an answer. I did not hear anybody say C. Am I right?
No C's.
I did not hear any C's. Okay, so with C, anybody want to offer why they eliminated C? So, yeah, why did you guys eliminate C?
Not negative. It would be negative at 0.
Wouldn't every slope have to be negative?
Pretty much.
Because there's no way for E to the negative X to be negative, so it'll be positive, but then the negative on the front guarantees that it'll be negative, right? And every single slope is positive.
So you'd have to do the dy dx for that one?
I don't think so. I don't think you have to do the dy dx at all for any of these. Have to. It could be helpful though. Could be helpful. Okay, so it's not C. I did not hear a D, am I right?
Right.
Okay, so D is out. Would anybody like to offer why they did not choose D?
It's not like the up, down, up.
But doesn't that sort of depend on which part of the period you're looking at?
Yep. Yeah.
Because like if you just look at cosine, then for a while it looks like it's all down.
Yeah.
But if you just look at a small part of it. This is looking at it from 0 to 3.
Okay, right. So it probably would be all up.
Say again?
So probably, if it was from 0 to 3, it would probably be all up. right, or no?
Well, see here, the derivative would be negative sine. So negative sine looks like this.
Oh, yeah, it goes.
With, this would be pi right here.
Okay,
So what do you think?
no.
It doesn't have to start at the origin though, right?
No, it doesn't.
Yeah.
It doesn't.
I don't know.
Okay.
Okay, so
You could do some test values, couldn't you?
Yeah.
You could do a few test values. Like, I think like pi over 4, pi over 2, pi over 3, pi over 6. Those would all fit within this. And so you could do some test values. I think you would see eventually that it's not D. Okay, so it's down to B or E. So let's do some test values to see if the patterns line up the way that we think they will. So I'm going to start off by plugging in x equals 1. So if x equals 1 for B, what would the slope be?
E to the 1?
E, right? And so E is roughly 2.7.
Yeah.
Okay, so that's right about here. So you look at that and you say, could those slopes be about 2.7? I have a hard time arguing against that, right?
Yeah.
It's like, yeah, could be, could be. So I don't know that we've learned anything at this point. And then we look at y equals e to the x, or excuse me, y equals ln of x when x is 1. So, we're going to be looking at this right here. dy dx equals 1 over x. So when x is 1, the slope would have to be.
1.
So again, it's like, is that really going to tell us? I mean, it could go either way, couldn't it? 2.7 or 1. It's really hard to tell what that column is telling us. So we're going to have to do another test value. Maybe we try 2. 2 would be over roughly there. Okay, so if I look at this one right here, y equals e squared, or y equals e to the x would be e squared for a slope. So e squared would be approximately what?
5.4.
No, that's just 2e. E squared would be 8 point something, right?
Yeah.
Ish, 8-ish. Okay, so you look here, and this is where I think we start to get this figured out. Because you look at that column, if the answer is going to be B, then those slopes would be around 8. Compared to the slopes at 1, they would be about 2.7. Are you seeing that the pattern is the opposite of what we'd want to see? So as x increases from like 1 to 2, then the slope of e to the x should also increase, and I see a decreasing pattern. If I try x equals 2 with the ln of x, the slope is 1 over x, the slope would be 1/2, right? So now we compare those, and I think we see that, yeah, the pattern going from a slope of 1 to a slope of 1/2 actually fits this slope field a little bit better. So I would go with E. I agree with, I think, the majority of you guys. E. So let me explain how I would do this. You can take this or leave this depending on what your level of memory is with these various functions. What I would do with this, I would probably do most of this just up here because I know what these functions look like. But if you want to get there, that's fine. So A is a parabola, right? So I'll just focus on the first quadrant. Does that first quadrant look like that slope field? No, it does not. B is y equals e to the x. That is an exponential that does that. Again, first quadrant, doesn't really agree at all. C is e to the negative x. So that is, again, an exponential, but it's decreasing from left to right instead of increasing. That feels like it's sort of right, but remember that all the slopes are negative. And all the slopes in our slope field are positive. So that doesn't work. D is cosine of x. So cosine does this. That doesn't look like the first quadrant at all, really, in any shape or fashion. And then the one that maybe we don't remember as well, E, is ln of x. ln of x is just the reciprocal, or I should say the inverse of the exponential. And you can see that in that first quadrant, it actually does look pretty good for the slope field. You can see that as you go from left to right, the slope continues to be positive, yet it decreases. So if you remember those like parent graphs pretty well, you could do this pretty quickly without having to do all the dy dx stuff. But entirely up to you how you'd want to handle that. Okay, so maybe armed with that, our final one for the day might actually be pretty straightforward for you. So let's see, let's look at the last. Okay, so the slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? Let me do a little zooming so you can see a little bit easier, perhaps. Yeah, that's too much. There we go. Okay, so we're thinking about this, trying to select an answer. You can either go to differential equations, or maybe if you're familiar enough with those various graphs there, you can make a judgment without having to do all those
So
differential
you can
equations.
just do the judgment of a graph.
Let's just shout it out. Go.
D.
G, huh? I heard D pretty loud from a handful of folks. D is definitely the correct answer.
No, it said A. I heard that. Not.
Why did you pick D?
Because it's cubic.
Cubic, yeah. Doesn't this look like a kind of a typical cubic? Yeah, so it's D. You could do the differential equation stuff, and but I really think that would be an unwise use of your time. If you can recognize that cubic, it's the way to go. Can I ask you a question? Let's say you're the quiz writer, you're writing this question here, and let's say you go back and you're like, you know what? I don't want to have y equals sine x be option A. Let's say you want to put in another function that will cause this to be a very difficult question. What function would you put in for A? Tangent, yeah. If option A was y equals tangent of x, doesn't cubic and tangent graphs, don't they look almost the same? I mean, of course, the cubic doesn't have the vertical asymptotes, but when you're zoomed into a certain level, you can't really tell. It'd be hard to tell the difference between the two. So that would maybe be a little unreasonable to expect you to discern between the two. Because honestly, out there on the left and right edge, doesn't almost look like a vertical asymptote. So yeah, I can't see why anyone would pick D over A or A over D in a scenario like that. So I wouldn't be too terribly concerned about that. Okay, that is it for the moment. Drew is convinced that the answer number 3 is D. I think he's. Oh, now he says false. He was trying to fake us out.
Alternative facts.
Hey, the clock's running, so that was recorded, just so you know. All right, what do you all think the answer is? The answer is A, yes. So what I'd want you to recognize here is this first sentence says, sugar dissolves at a rate proportional to the amount present. We're assuming here that S stands for the amount of sugar, and T stands for time. What does the K stand for?
Constant.
It's a constant, right? That's going to be the proportionality constant that tells us how quickly the sugar is dissolving or how slowly the sugar is dissolving. And this is actually pretty realistic for sugar dissolving, right? Yeah. Okay. So then I thought we could also talk about number 4, and then maybe we'll do a little bit of work to connect 3 and 4 a little bit, and then we'll do one last one, and that'll probably be a pretty good time to stop, or at least close to it. Okay, so number 4 looks really similar to number 3, but it's importantly different. It says the rate of change of the number of bunny rabbits in a field is proportional to the number of bunnies in the field. Is that phrase starting to get burned in your brain a little bit this morning? The rate is proportional to the amount that's there, essentially. Which equation describes this relationship? Instead of a bunch of differential equations now, these are solution curves, right? So this is a little bit of a different question. So this would require a little deeper connection for you to make. So think it over, discuss, and we'll get an answer in a moment. Something other than B. Everybody thinks it's B. Okay, now that's encouraging to me because that means maybe you did watch the video. Maybe you did, because that is the solution to the differential equation. I completely agree with you. Is it okay with you guys? Let me just see something real quick. Is it okay with you if I prove this again to you? Maybe we prove this to each other?
Yeah.
Okay, so here's what we could do to prove this relationship to be true. And this skill is useful. This skill that I'm about to show you is very useful. We're going to want to be good at this. We'll practice it a lot more in the next section, but we want to be good at this. So if I look at this phrase right here, the rate of change of bunnies is proportional to the number of bunnies in the field. I can interpret that as a differential equation. This is similar to the previous one. I would write this down as dB dt equals k times what? B, that's right, equals kb. B stands for the number of bunnies, k is a constant, dB dt is the rate. So the next thing I would do, if I'm going to solve this differential equation, what do I have to do? Separate the variables, right? So k is just a constant, so I'm going to leave that on the right side. But the b needs to go over, so I'm going to end up with this. dB over b equals k times dt. Does that work? Again, I want to remind you, k is a constant, like 2 or 7 or -1/2 or whatever. That's very important that we remember that. Once you've separated the variables, what comes after that? Integral, yep, we're going to find the antiderivatives of both sides. So what is the antiderivative of dB over b? ln of b, yes. ln, technically, of the absolute value of b. In this case, I'll explain why the absolute values are not going to be hypercritical, but in other cases they could be. So let's keep that in mind. What's the right side? If k is a constant, kt, that's right. Kt plus c. So this is where sometimes it gets a little confusing. K is a proportionality constant. C is the constant of integration, right? So they're both constants, and conceivably they could be the same. They're probably not, because they could be any number and they could be different numbers. Okay, so my goal now is to solve for b, like you saw in all those options. What would we do? Like, what algebra step would we take?
E.
E, yep, we're going to e both sides. So e to this, e to that. And that would give me, on the left side, just absolute value of b equals e to the kt plus c. Now, in my next step, I'm gonna lose the absolute values, and it's not going to be for any like random reason. It's going to be for a very specific reason. The reason why I can drop the absolute values is because I know that b stands for the number of bunnies, and there's no way you can have a negative number of bunnies.
You might want negative bunnies.
You might. You might want to throw negative 10 bunnies into a field and get rid of 10 other ones, I guess. Whatever. My point is, because here's the more important point, guys. Because the initial condition could never have a negative b, the absolute values are going to have no effect. Every now and then, maybe not in this situation, but other situations, they will have an effect, so we can't ignore them. But here we can, I think, successfully drop them for that reason. The number of bunnies is going to be non-negative, right? It has to be 0 or more. Okay, and then on the right side, can I remind you of an old algebra rule? If you are adding exponents, you are really multiplying your bases. Yeah. So this side would be e to the kt times e to the c. And let's just remember, yeah, that e is a constant and c is a constant. So e to the c would just be some other constant. And so we could replace that with a different constant. So it'd be e to the kt times c. Or ce to the kt. Same thing. And so then that would allow you...
Because do you want us to change the
Like the
C,
C2 or
like a
whatever.
C, like a subscript or something, because it's like different?
So, yeah, so that's a really good question. So you'll see this noted sometimes. The way that I'm going to show you to deal with this in the future, it's not really going to matter too much. Sometimes you'll see this noted. Like you'll see somebody will write C1, 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 C2. And they'll make a little note to the side that says C2 equals e to the C1. Right? And that's obviously really good notation. I'm going to show you a way that kind of like circumvents that to where you don't really have to do that. But you might kind of maybe find some college professor in the future that's going to want you to specify those things. Based on how we do things, it's really not going to matter too much. If you kind of go off track from how I show you to do it, then that sort of thing could be really important. But I'll encourage you to stay on track. So, yeah. Good questions. Anybody else? Okay, awesome. Well, let's do our final question of this section, and that's number 5, I guess. Let's see. This would kind of be the full go here. It says a substance decays at a rate proportional to the amount present. If that's not burned in your brain yet, hopefully this one more time will further reinforce that phrase as being a very important phrase. So I'll underline that for you. It says, if 30% of such a substance remains after 16 years, what is the half-life of the substance? This is a very sciencey application, and this is actually a pretty realistic application. By the way, many people, hey Drew, and others, I want you to hear this. Many people subscribe to the idea of carbon-14 dating as a reliable way of seeing how old something is. It's presupposing you know how much carbon is in there, and I don't want to get into the the truthness or the falseness of it, but many scientists do rely on that. I want to point this out, that that's more or less what this is modeling, that sort of thing, like the decay of something. This is really talking about radioactive decay, so this would be a little more deadly than carbon-14. decay, but we're talking about a substance decaying over time due to entropy and just the breakdown of the molecules and the atomic bonds between whatever substance we're talking about. So this could be like plutonium or uranium or something. You guys know, like if someone came in here with like a chunk of plutonium and just like set it on the table, like we wouldn't survive, right? We'd eventually all die of something terrible, maybe cancer or worse, right? Because it gives off gamma rays and alpha waves and things like that because it's decaying, right? And it's sending off a tremendous amount of energy just by sitting there. So that's kind of what this is talking about. So anyway, so here's my first task for you guys. Will you take this phrase right here, a substance decays at a rate proportional to the amount present, and will you guys write a differential equation for that, right? So a substance decays at a rate proportional to the amount present. I don't know what letters you're going to use. We'll maybe try to come to an agreement on that here in a second, but see what you come up with. Excuse me. Okay, let's see here. Alex, did you write down a differential equation for this? What'd you write down?
I just did ds, dt equals ks, just for s for substance.
Sure. Yeah. Do you guys use S's? Anybody use something different?
No, we
I
use
use an
A.
A for amount.
A for amount. I'm fine with that.
No, though.
I'll go with S because he said S,
It
but
says substance in the question.
It says it is
It's
a
an amount in
substance.
the question too.
No.
okay. So let's say, guys. Hey, listen. Shh. Hush. Let's finish this up. So it says 30% of such a substance remains after 16 years. What is the half-life of the substance? I want to point something out to you guys. There is some key wording that we've talked about a little bit. We talked about it quite a bit, and we're going to talk about it a lot more in the next section. It's kind of fortuitous that it's sitting right there. Notice the next section says solving differential equations by separation of variables. Please notice that in number 5, it doesn't say, find the solution to the differential equations, make sure you separate the variables, find the particular solution. It doesn't use those key phrases. So I want to let you guys know, when you see those key phrases like find the particular solution or use separation of variables, all of those things mean that you need to show a lot of key steps. The ones we've practiced a lot, right? So that shouldn't be a big shock. Notice in number 5, it doesn't say anything about that. It simply just asks a pertinent question to the topic, right? So in a case like that, I am okay with you doing this. I recognize what that is. I know that my solution curve will be this. S equals CE to the KT. So all those steps where you separate the variables and do your antiderivatives and separate out the, adding of the exponents and solving for S or B like we did before, because it didn't say show all your steps, find the particular solution, separate the variables, because it didn't use those keywords, we can just jump to what we know to be the solution. The good news is this. Let's say you're doing this question and you space out what the solution is. Can't you still get there? You can still derive this, but in cases like this where it doesn't say show all your steps and all that sort of stuff, you can just jump directly to the solution curve. That's okay. All right. So it says if 30% of such a substance remains after 16 years, gosh, what do you think we do with that? 30% of the substance remains.
Wouldn't be point three.
So the time is clear, right? T is 16. So I'm going to go ahead and write e to the k times 16. But how do we deal with that 30% thing?
Wouldn't it make K 0.3?
It doesn't make k 0.3. That's not a bad guess, though. Say that one more time.
SB1 and CB.3.
It'd be the other way around, potentially. Let's talk about it in a little more detail here. S stands, as you guys know from before, from what it says, is S stands for the amount that's there, right? For those of you guys that maybe have had science classes, maybe you remember that C stands for the original amount. Or you could say the amount is time equals 0. The amount when T equals 0. So what I would do is something like this. Maybe write S over C equals, I would just divide both sides by C. So if S stands for the amount that's there, and C stands for the original amount, what would be the value of S over C when T equals 16 years? 30%. Does that make sense? Whatever S is, it's 30% of C. We don't have specific numbers for it, but we know that the relationship between the two is 30%. So 0.3 is equal to e to the 16k. Now we got to find k. How do we get that k out of the exponent? ln, that's right. So ln of this, ln of that. That would give us ln of 0.3 equals 16k. So in your calculators, maybe you do ln of 0.3 divided by 16. That'll give us our k value. Be really careful about rounding these. Let's get the whole number. What do you got up there, Dixon or somebody's? Let's get the whole number.
Don't round.
Don't round. Negative point
Point 075.
07. Is there more number?
5248.
Is there more number? That's it?
Yeah, that's all I have.
Stops
I
right
got
there.
I mean,
2483003.
Yeah, that's what I have too.
So when I say whole number, I don't mean most of it. I mean all of it. You want to keep all of it because when we're talking about exponential growth and decay, for your exponent to be cut off is going to have a pretty large effect on the end result. Okay. So my final task then is to answer the question, what is the half-life? So what I'm going to do is take that k value that we just worked so hard to get, and I'm going to write S equals CE to the negative 0.0752483003 T. Use your calculator to store that, if you will. And you don't have to write that out every single time. Just store it in your calculator and make sure that you can use it later. Okay, so we're asked what the half-life of the substance is. Half-life is a time unit. And so it is the time needed for the substance to decay to half of what it was originally. So half, what percentage does that sound like to you? 50. So if I do that S over C thing again, what do you think that would equal?
0.5.
So I would write that. I would write 0.5 equals e to the negative 0.0752 ... whatever that number is, t. And I got to just solve. Oh, yes, sir.
Right there, would it be okay if we wrote K? Because right above it, it says K equals that.
Sure.
Okay.
Just keep it stored in your calculator, but I'm down with that. Yeah, that makes a lot of sense. So how do we get the t out of the exponent? So yep, ln of 0.5 equals negative 0.0752 whatever t. So then all you do now is divide both sides by that negative 0.0752. What do you come up with?
9.21147
Is there a decimal or a 10 power involved with that?
No, it's just 9.21.
9.21? Let's go 3 decimals just to
9.211, yeah.
9.211 equals t. So the half-life would be 9.211. Do you guys agree with that figure? For those watching the video, I hope you
Years.
agree. Yeah, it'd be years. That makes sense. That fits the data. So, all right, awesome. Hey, have a great rest of your day. No video for tomorrow. See you then. Lord willing.